Some of you may know this, some of you may not. I used to be a TA for an embedded systems project course at my university for 2.5 years. And every semester we got the students to do a different embedded project. So if you're wondering about, what projects I should do to break into embedded, this is what we get students to do at a real university to improve their skills in embedded systems. So first off, I claim no rights whatsoever to these project ideas. I didn't come up with them. It was our wonderful and very talented head of teaching staff for this course. We're just going to go through what the project idea is, what some of the requirements of the project were, what kind of hardware devices you need, and what it kind of teaches you, why I think they were valuable for students to learn, so that it kind of ties back in with my previous video, which was just a general overview of the entire embedded field. Has everybody heard of Guitar Hero? It was a pretty popular game back in the late 2000s, early 2010s, and a Guitar Hero clone as an embedded device is the first project that we're going to talk about. So essentially what I want you to think of is the Guitar Hero guitars. What do they have on them? They have these 4 big buttons, and you have to press them in time with the music, okay? So what we're looking at here is essentially we ask students to make these Guitar Hero guitars. Of course, we don't expect them to make a full OpenGL game to go along with it. So instead of it being on, a computer game or whatnot for the display, we got them to do the notes kind of showing up on an LED matrix. I'll put an example of an LED matrix up on the screen if you don't know what one is. This was a really fun game, a really fun project for students to do because, of course, it's not just a project, it's a game. So while you're developing it, you're playing a game. It's got rhythm, it's got music. It was a really and at the end of it, you come away with a game that you can play, that you coded. It's really, really cool. It's really cool. So what was involved with this project? In terms of firmware design, there was a lot of timing involved. So if you think about what students kind of had to do here, you're keeping track of a few different timing information. So the first timing information you're keeping track of is the beat of the song. So every time the song has a beat, you shift the notes down on the LED matrix and the user gets ready to push the buttons on their device. Then you have to actually measure how close the user was to that beat and give them a score. So you have perfect is obviously you're right on the beat. You have good, which is, okay, you're kind of near the beat. You have okay, which is like obviously not the best, but it's possible. And then you have bad and miss, which you either were pretty bad or you completely missed the beat whatsoever. And so you have to compare the time that the user pushed the button to the last beat of the song. And you have to say like, okay, how close were you? And of course you can be in front of the beat or you can be behind the beat, right? So there's a lot of timing and stuff going on here. And of course, because you're trying to measure things in a very precise way, it teaches students a lot about interrupts. And because polling for something where you have to be this accurate maybe isn't the best idea design-wise. Anyway, so timing and scheduling were a big thing, interrupts were a big thing, and a user interface / UI was another big thing. So what I'll say is that in every project we get the students to do, there is a user interface. There's a LCD or OLED display where they have to let the user do things. In this case, it's like, okay, we have all of these songs on an SD card, and the user gets to look through the songs on the display and pick them out with buttons, right? So you have a user interface in there as well. Another really useful thing that I just mentioned there was the SD card and files. One of the things that students had to do was pass WAV file metadata. So that's a very important thing for people to learn. It's like, how do I look at a file and I look at the metadata of a file, and how do I actually get useful things from that? That's actually a very good skill to have, and I think it was great that students learnt that in this particular one. So let's go over some of the hardware that you would need if you want to do this project, because honestly, I think it's a great project, and it's a lot of fun. And it's a good introductory project if you're looking to get into embedded because it is so much fun. Obviously, for the user interface component, we can break this into blocks, right? So for the user interface component, we're looking at buttons. You need at least 4 colored buttons, for the notes. You need buttons for the user interface, like song selection. You can reuse the note buttons if you like, that's a perfectly fine thing to do. You need LEDs to display the notes as the song progresses. You need an OLED to display the song, or an LCD. You've seen those kind of blue looking LCDs to display song metadata, and maybe the score, or like what the user, did you get a perfect? Did you get a good? Did you get an okay? Things like this. You need a speaker and a DAC, so digital to analog converter, to play the sound, or alternatively, like we got students to play sound in the advanced course, right? Because what I'll say is we have 2 levels of courses that I TA'd for. One is a more advanced embedded project course. It's aimed at 3rd-year students. One is an introductory embedded project course. It's aimed at 2nd-year students. The 2nd-year students got to play their audio from a desktop computer, right? So they essentially just synced it up with when they started the song on their device, but we expected the more advanced students to be able to play the audio from their device. So of course it's up to you how advanced you want to take it. If you want to play the audio from your own device, you'd need a speaker and a DAC for that. Now, you obviously need an SD card reader, and you need some WAV files. And you can power this thing off a battery, or you can power it off of USB. All right, so we got students to power it off a battery, but there's no reason you can't power this thing off of USB if you don't have that kind of requirement. So for all of these projects, keep in mind the introductory course that I just mentioned. We got students to use an Atmega 328P, which is an 8-bit AVR microcontroller. It's very old. It's a great tool for learning because it's very well documented. It's actually the same micro that's used in the Arduino Uno. So if you kind of want a 0 to hero, I would strongly suggest you use what we do in the advanced course, which is STM32s. And you learn the STM32 ecosystem because that's an ecosystem that is widely used in the industry. The next project I want to talk about that was really valuable was building an oscilloscope. If you're not familiar with what an oscilloscope is, maybe if you're new to the electronics engineering field, it's a very fundamental electronic tool for analysis of signals. What you do is you are measuring, for example, a voltage. This is what we got them to do. Measure a voltage and display it on a graphical interface. So if I have a voltage that is varying like a sine wave, like sinusoidal, then I will be able to see that on my oscilloscope display. Instead of just reading a voltage, like, maybe it starts at 0 volts and then goes up to like 1 volt and then 2 volt and then back down to 0 volt, it will actually show me, like in, for example, like desmos.com, it'll show me what that signal actually looks like as it varies. And this is really, really cool for students to do because it shows them how like basic fundamental lab equipment actually works. And on the oscilloscope, you can do all kinds of mathematical analysis, like what's the peak voltage, what's the frequency of the signal, things like that. Anyway, enough about that. Everybody knows what an oscilloscope is now. Let's get into how this thing actually worked. So just like before in Guitar Hero, we have a user interface. In this case, we're using a bigger screen because we want to do a sort of little mini graph on this display so we can see what our signal looks like. And this is a really cool thing to do because it teaches you a lot about embedded graphics and embedded UIs and a little bit about frame buffers and things like this, because you essentially have to make your own little graph engine, right? Which, to be fair, I don't think is particularly hard, but it's a cool problem to be able to solve. And you have to display that on an LCD. So I think that's pretty cool. You learn a lot about embedded graphics, you learn about embedded user interfaces and things like this. Another very, very amazing thing that this teaches you about is analog to digital. So obviously, I talked a lot in my previous video about analog to digital and digital to analog because the real world is analog, guys. I can't stress this enough. We live in the digital world when we program computers, but the real world is analog. And building an oscilloscope teaches you a lot about the analog world. and how to use analog to digital converters. So let's go through some examples of this, right? If you're using an STM32, some of them will have analog to digital converters built in. Otherwise, you can buy an external ADC that is maybe on I2C or SPI, something like this. So it teaches you a lot about how analog to digital conversions work. And that's really, really excellent. It also teaches you about data streaming, because in this case, one of the things that I will suggest that you do is be able to stream this data over a USB connection to a computer. So maybe in like a JSON format or a CSV format or something like that, you essentially stream the data points back to a computer so that you can open it in Excel or something and visualize it on a computer. That's something we got the students to do. Was it had to connect to a GUI application, a custom GUI application on the PC. And it's very valuable to learn how to pack data, how to send it over a wire, how to send it efficiently, you know, because we had like a sample rate, like you have to have this sample rate for the live data streaming and things like this. So it's good for learning how to send things over a wire. Also, you have maybe some op amps in there as well. So depending on how crazy you want to get with it, just be aware that all of these electronic components have a voltage tolerance range. So for example, your ADC might only be comfortable with 0 to 3.3 volts. What if I want to measure a signal that is 10 volts? Well, in that case, I have to apply some analog scaling to that with op amps. What if I want to measure a negative voltage? Well, if I want to measure a negative voltage, then I have to apply a DC offset and shift my voltage upwards to sort of bring it into the positive range. And you can do that with op amps. So depending on how advanced you want to make your oscilloscope, you can add all kinds of analog op amp configurations in there to help you measure more kind of exotic quantities, right? Which could be a really fun experiment for you to play around with and learn how to use op amps. Now, this thing would be powered off of USB because we want that data streaming functionality, right? So you're going to have a USB connection. Let's talk about the hardware that you're going to need to do this project. You're going to need buttons and a big fat LCD for the user interface, right? Because we want to show what this signal is looking like on our big fat LCD. But other than that, that's pretty much it. You might have a button that says like start or stop recording on the device. You could have a flash chip, like you could save some of these logs to flash in addition to streaming it live. You'll need a microcontroller that supports USB, or you will need a like a UART to USB converter. Those are actually pretty cheap, and it's more simple to set up than USB if you buy one of these. But on STM32, USB is quite simple to set up anyway. So you'll need one of those. Like I would recommend doing like a USB CDC, like virtual COM port kind of thing, and then you can open it in Python with something like PySerial. Something like this, you know. Now we're going back to something that might actually be pretty useful for you. We're talking about a macro keypad. This is a little number pad shaped device, kind of like if you've seen an Elgato Stream Deck before, where each key performs a number of different actions, right? Not just one action, it performs a sequence of actions. That's why it's called a macro keypad. So this is a really cool project and pretty useful, you know, because at the end of it, you have your own macro keypad that you can configure macros to do whatever you like, you know, like it might automate some common basic tasks that you encounter on the daily. I think it's very popular, these macro keypads with video editors and photo editors and people like this. Anyway, so for this project, you are going to learn about button input handling and button multiplexing. So a very common thing that you'll notice is like, what if I have more buttons than microcontroller GPIO pins? And this is where button multiplexing comes in. I will put an example of one of these circuits up on the screen to be able to read more buttons than you have GPIO pins. Of course, you could just cheat and buy a microcontroller that has enough GPIO pins if you don't want to bother with something like this. So you'll learn about buttons, you'll learn about button multiplexing. Speaking of which, you're going to need some like mechanical key switches, which are pretty easy to come by. And some of them even include really cool things like LEDs. So if you want to spruce yours up a little bit, you could always include support for these LEDs. I think they're like W82S, whatever the very common one is, and they're not super hard to configure. So if you want to spruce your keyboard up a little bit, you could buy some of these key switches that have the LEDs built in. So you'll get some of those. You'll need a direct USB connection, because one of the things this is going to teach you is about the HID USB protocol. HID stands for Human Interface Device. HID is used for all kinds of things, from like mice to keyboards to touchscreens. It does exactly what it says on the tin. It's a human interface device, and that is what you're building. So you need to build something that speaks the HID protocol, so you'll learn about that. And it kind of teaches you how keyboards work, right? Which is a really cool thing, So you'll notice that like one of the common themes among all of these projects is like, at the core, they are supposed to teach you fundamentally about how common everyday embedded devices could be made. And that's to open your mind up to the possibilities. Because if you haven't seen one of these things before, like you probably look at a keyboard and you're like, this is a complete black box. I have no idea how this is working. How would you even begin to make a keyboard? And then you get thrown into one of these projects where it's like, okay, you're building a keyboard, which is really cool. Another thing you'll learn about is user configuration and flash storage. So here's the thing, guys. If your macros disappear every time you unplug the power, you're not going to have a very useful macro keypad. So you have to learn how to store these user configurations in some form of non-volatile memory. In this case, I would say flash or EEPROM, depending on what microcontroller you go with. So these kinds of things are all very useful, and this is a fairly chill project electronics wise. So if you're looking for something if you're not so confident with your electronics and you want something a bit more chill electronics wise, then this project may be for you. I will note that you're going to need a voltage regulator, because USB power gives you 5 volts and a lot of chips cannot handle that. So you're going to want a voltage regulator set up in there to bring you back down to 3.3 volts. But this is a really good thing for you to learn, because it'll teach you about voltage rails and about how to regulate voltage, which is another really important thing for embedded developers to know.